Okay, welcome to lecture here. We'll get started in just a second. And again, we'll be picking up here 17, I think, maybe, or whatever chapter this is, 19. I think it's 17. And then we'll be going on to chapter 18, which I think is next. And again, those notes are up online if you need them. Just grab a couple things here. Okay, so where we left off was we're sort of finishing up really talking about thermodynamics and free energy. We saw a couple of equations and formulas that related sort of delta G to sort of non-standard conditions. And that was our delta G equals delta G naught plus RT natural log of Q. And we also saw that under equilibrium conditions, that formula becomes delta G naught equals minus RT natural log of K. So as we talked about with a lot of these sort of formulas, what you want to do is really sort of the best approach is sort of use the formula that has the information that's given to you in the problem. So as we talked about, if you're under non-standard conditions or something like that, which again, a reminder is pressures are not 1 atmosphere, concentration is not 1 molar, temperature perhaps is not 25 degrees. You would want to use that one with the Q in it. Again, maybe not under equilibrium type conditions. Something to do with equilibrium would involve either calculating the equilibrium constant or you're given an equilibrium constant. Then you would obviously want to use the other one as well, the one with the K in it, the minus RT natural log of K. So I think we finished up the last example. So I think we're on this example. So why don't you take a couple minutes here and work this one out. We're looking for this one here, the delta G naught, if the KSP is 1.7 times 10 to the minus 6. So see what you come up with there. And then we'll talk about it in a couple minutes. Okay, so again, in this case, we are given a KSP. Remember that although it is technically a KSP, they're all really just K values, no matter what they are. KA, KB, KW, KSP, they're all the same, which means obviously we're looking for delta G naught. So we would want to use that equation that contains the K value in it, which is delta G naught equals minus RT natural log of K. Remember that the R that we use is the gas constant that has to do with the energy. So that's 8.314 joules Kelvin mole. temperature, like pretty much everything, needs to be in Kelvin. So we would want to add 273 to that. And that's going to give us our 298 Kelvin. And at that point, I think we got pretty much everything we need. We're going to go minus R times our 298 Kelvin, natural log of our K that was given to us, which is 1.7 times 10 to the minus 6. So if we put all that in, carefully, I suppose, 1.7 negative 6 times 298 and times 8.314. Also make sure you make it negative, the negative front. And that should give you something like 32914. That would obviously be joules per mole. And again, since delta G is typically given in kilojoules, you can take it to 32.9 kilojoules if you like. Any question on that calculation? Again, much like a lot of the things that we've been talking about sort of in this chapter as well, we can, see if it does make sense. So if our value does make sense in what we got, and if we look at our K value, which obviously is a KSP, and as we're familiar with KSP, they are very small values for K, which means when you reach equilibrium, you mainly have your reactants. And thus, with a 32.9 kilojoules that's positive, that would imply that this reaction is non-spontaneous, which means that this reaction really is not proceeding to the products, which would make sense since it will be kind of staying on the reactant side. Any questions on that calculation there? All right, you got, I think, one more here to go. So for this one, the delta G naught is 2.6 at 25 degrees in one experiment. Initial pressures, 4.26, 0.024, and 0.23. Calculate the delta G for this one and predict which way the reaction will actually go. So take a couple of minutes, see what you come up with on this one. Just keep dropping stuff. I'm sure that sounds great on your end. Okay, so let's see how we're doing. So here we're given the delta G naught. We're actually looking for the delta G. So that really should be sort of a big hint that you need to use this equation that we saw, or formula that we saw earlier, RT natural log of Q. The other big hint is we have all these partial pressures given to us, which is kind of what the Q is for. You could also obviously have some type of concentrations given to you. Remember that Q is just like what we do with K, right? So we, in this case, would be the partial pressure of HI, and we need to square it because of the coefficient divided by the partial pressure of H2 and the partial pressure of I2, which we do have all these. We also see that these are not 1 atmosphere in terms of pressures, which would imply that it is not standard conditions, right? Because standard conditions, 1 atmosphere, is what we deal with when we talk about pressure. So again, those are some hints that you can kind of see in a problem to kind of help guide you, hopefully, to the right sort of formula. Other things that we do want to watch out for as well is units. We got this guy that's in kilojoules. This guy's in joules. So again, you need to do some type of conversion. Otherwise, you're going to run into some issues there. So let us maybe flip the page here. So I got something to work with. There we go. So if we just take all that and we take our delta G equals delta G naught plus RT natural log of Q and kind of stick it all in. What I'm going to do is take my 2.6, which is my delta G naught. I'm going to multiply by 1,000 like I've done before. Again, that's going to convert for me into joules. The other option, obviously, is to convert the R into kilojoules, whichever way you want to do it. R would be 8.314 joules in that case for me. Temperature was 25 degrees, so again, that's going to be 298. And then we're going to take the natural log of our Q. So our HI squared was 0.23, the pressure, and we're going to square that. And we have 4.26 for our other pressure, and our other reactant pressure was 0.024. So again, this right here is Q, yeah? So that's basically Q. All right, so if we do all that good stuff there, we are going to end up with a number, perhaps. Let's see. We'll end up with, it looks like, 967 joules. Or again, since it is a delta G, that would be 0.967 kilojoules in that case, if you like. Didn't really specify, so technically speaking, you could go with either unit that you like. Per mole, if you'd like to put that in as well, probably should go there. As again, technically speaking, the kelvins here cancel, so still have the moles over there. Any question on that calculation? That will also tell us that when we look at it, our delta G here is a positive number, which means that this reaction is non-spontaneous, the way it's written, which means technically speaking, it would be going this way towards our reactants, right? As a non-spontaneous process, obviously, it would not be going towards the products. Any questions on any of that? So again, as we sort of talked about, this equation here or formula here, sort of used to calculate delta G under sort of non-standard conditions. Again, could be something like, as we talked about, something to do with the pressures, like in this case, something to do with concentration, something to do with temperature, sort of your three sort of big ones that are necessarily not standard conditions. And again, just a reminder, a rundown, that's sort of table type conditions, a lot of times where you see those little knots next to those things like delta G naught, delta H naught, and all those type of things. Again, 1 atmosphere, 1 molar, and 25 degrees Celsius are sort of our standard conditions for most tables that you look up for. Those are sort of the conditions that are happening at that point. Any questions on that there? And if I'm not mistaken, that should wrap this chapter, I think. Yes, sir. All right. We are then going to roll into the next one, which I said is up there, the notes up online if you need them. I think it's chapter 18, some electrochemistry. So just give me a second to kind of get it going, and we'll get started on that one there. Okay, so hopefully that is full screen for you guys. I hope it's kind of weird sometimes. Okay. All right, so we're gonna pick up here. It's not okay. Let me try it again. It's like weird sometimes. Hang on here. All right, let me see here. Is that any better? Nope. All right, just give it the old college try one more time from the beginning. Go. All right. How about now? Good. Hopefully, yes. Okay. Sorry about that. It's like weird. It's like it looks right on my side, but sometimes it doesn't translate. It's kind of weird. Okay, so we're all good then. Perfect. All right. Okay, so we're off to chapter 18, and again, it's electrochemistry, and we're going to be talking about obviously mainly galvanic cells and some electrochemistry, a little bit about batteries in this chapter. We're also obviously going to talk about redox reactions, which is essentially, what this is all about is our redox type of reactions that occur. So just to make sure, so everybody's on the same page, we are going to kind of go over some of the basics of obviously electrochemistry in terms of redox reactions, also in terms of how to balance redox reactions properly, half reactions, reducing reagents, reducing agents, oxidation numbers, and all that kind of stuff. Just to make sure, again, everybody's sort of on the same page. My experience, I guess, depending on who you maybe had for the first part of the class there. You might have got a lot of it. You might not have got a lot. So again, hopefully we'll all be on the same page. So I apologize if some of this is review for you, but hopefully it'll be a good review. Again, that way at least everybody will sort of be starting in the right spot or the same spot. All right, so when we talk about electrochemistry processes, it's really oxidation reduction reactions that are occurring. And when we talk about redox reactions, those involve that process of oxidation and reduction. And as you may be aware of, when we talk about oxidation, that typically means that something has lost electrons, while reduction means that something has gained electrons. And sometimes people remember that, like Leo the lion goes grr, losing electrons oxidation, gain electrons reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You could choose both, I suppose, and not have to worry about it. But that's a good way to remember it. Also, a very good way. Sometimes people get really sort of not 100% sure of what is being oxidized, what is being reduced. And a really simple way you could kind of do that is kind of like just to do a basic sort of number line, if you will. And on the right-hand side of 0 is typically positive numbers, left-hand side is negative numbers. And when you lose electrons, you typically become more positive. So that is oxidation occurring as you head in that direction. If you're kind of heading in the opposite direction, becoming more negative, that's where reduction occurs. So we can, just simply almost just follow the path, whichever way you're kind of going, and you can basically figure out what is being oxidized, what is being reduced. Now, when we do these things, these are really involving electrons being transferred, and as electrons are transferred, they can be used for some type of work. Like, for example, batteries, right? So electrons are transferring, goes out through a wire, power some type of device. We could also apply sort of a battery or something like that, or an electrical current to cause a non-spontaneous process to occur. And that's something that we see in electrolysis type problems, which we'll talk about at the end of this sort of chapter. So if we have a reaction like this is really a redox reaction, although most people, when they look at it, they do think of it as a synthesis or combination reaction. The oxidation state of magnesium would be 0. So again, we'll talk about how to assign those in just a second again. But anything in a standard state that's uncombined will have an oxidation state of 0. O2 is also going to be 0. Again, that's naturally how it comes. And if we look over here, when the magnesium and the oxygen come together, that's really when they gain charges. So this is +2, and this is going to be -2 in this case. And what we see is, again, in terms of the magnesium, again, how you can use this little guy is magnesium started at 0 and pretty much ended at +2, which means it's heading in this direction, which means that it is going through oxidation. Oxygen also started at 0, but it ended at -2, which means it is heading in this direction, going through reduction. So, it's a very easy way to sort of figure out what is happening in terms of what is being oxidized and what is being reduced. In this particular case as well, these are what are referred to as the half reactions. And this is the oxidation half reaction. This is the reduction half reaction. And they're called half reactions because essentially, if you basically put them back together and add them together, you get the overall reaction. And again, if you do that, what should always happen when you add up half reactions is the electrons should always cancel out. So they always should end up being on opposite sides. So these 4 electrons would cancel. That would leave us 2 magnesiums plus the oxygen. These 2 ions will come together to make 2 magnesium oxides. So again, that's the overall reaction. Oxidation half reaction means that those electrons are being lost, like they're being given off. So that is how we recognize that as the oxidation half reaction. We see that the electrons are on the product side. While the reduction half reaction is opposite, reduction means that essentially those electrons have been gained. So the electrons should end up on the reactant side in a reduction half reaction. And again, the basic definition of oxidation is pretty much what we just talked about. There is there are some other sort of definitions of oxidation and also reduction. So when we talk about oxidation, the one that we deal with the most here in sort of general chemistry is that one about the loss of electrons. When you get into something like organic chemistry, oftentimes it's a little bit hard to follow those electrons being lost and gained because you deal with a lot of nonmetals. So the gaining of oxygen as you go from reactants to products is another definition of oxidation, and the loss of hydrogen, or H2 really, as you go from reactants to products, is a third sort of definition of oxidation. Again, these two mainly you see more in sort of OChem. General chem, we usually focus more on sort of the gaining and losing of electrons, and reduction really does have sort of the opposite definitions. So as we talked about, the gaining of electrons, which is mainly what we deal with here, but it could also be the loss of oxygen as you go from reactants to products, or the gaining of hydrogen, which again is usually H2 as you go from reactants to products. So if you continue on to sort of OChem or something like that, you oftentimes will see more so oxidation and reduction sort of spoken in terms of hydrogen and oxygen basically happening. The numbers above the everybody in the last slide was the oxidation numbers. So the oxidation numbers, again, are I'm assuming you're talking about these numbers here that I kind of circled out. Those numbers are what I refer to as their oxidation numbers or their oxidation state. And we're going to talk about how to assign those in just a second. But essentially, it's sort of the charge they would have if there was sort of a complete transfer of electrons in this situation. And as we might have touched upon a little bit, I think when we were talking about sort of acids and assigning oxidation numbers, those are not necessarily always the same as the charge we normally think about in terms of elements. So for example, we'll see something like nitrogen where we normally think of it as like -3, but in certain situations it could actually have a plus sort of oxidation state, and it just depends on sort of the situation and what it's bound to. So in a few slides down the road here, we'll talk about how to assign those. Here's another one with our calcium. And again, if we look at what's happening here in terms of those oxidation states, this is by itself in its natural state, it is 0 in terms of oxidation state. The O2 would also be 0. Again, when these two come together, that's our metal nonmetal, and that's when it's going to gain charges. So +2 and -2 here. So again, essentially, if you sort of follow what's happening, if you weren't 100% sure, that's not minus. The calcium starting at 0 and going to +2, which is in that direction, which means our calcium is going through oxidation. The oxygen is starting at 0 and heading to -2, which is in that direction, which means the oxygen is going through reduction in that case. Here again, when we have those half reactions, here's our calcium losing its electrons. It actually, in a balanced situation, loses 4 electrons, 2 per calcium, right? Which is why calcium is +2. And in terms of our oxygen, it gains those 4 electrons. These things always happen together. These oxidation and reduction reactions always happen at the same time. So the good news on that is if you could identify what is being oxidized, you could also identify by default what is being reduced, or vice versa. So if you can only really determine one of those things, it's okay, because you can use it to figure out what's happening with the other one. The other important thing is it's a complete transfer of electrons in this sort of situation. So whatever electrons were lost by the calcium should be the same number of electrons that were gained by the oxygen. So as I mentioned earlier, when you balance sort of basic redox reactions, you always need to make sure you have the same number of electrons in each half reaction before you add them together. So for example, if the top one only had 1 electron and say the bottom one had 4, we would have to multiply the top one by 4 to get 4 electrons in each before we added them together. Now, another thing that sometimes confuses people is the idea of reducing agents and oxidizing agents. So the reducing agent is the guy that gets oxidized. So our reducing agent is the substance or species that is actually going through the oxidation reaction, while our oxidizing agent is actually the guy that is being reduced. So when you're asked about the agents, they're talking about really sort of opposite of their names. So again, that oxidizing agent is the thing that gets reduced, while the reducing agent is the guy that gets oxidized. The reason for that naming is because that is what they cause to occur in the other substance. So in order for your something to be oxidized, it has to lose electrons. So if something's going to lose electrons, something's going to gain electrons, right? So the guy that's going to gain electrons and be reduced will cause the oxidation in the other species, and vice versa. If something's going to get oxidized, it's going to lose those electrons, which means somebody could gain those electrons and become reduced. So again, the agents are the opposite. By the way, the reducing agents and oxidizing agents are found over here on the reactant side of the equation in most cases. So that's where you find them. And you do usually want to be a little bit specific about what you're choosing as sort of your oxidizing agent, reducing agent. So if we go back and look at a couple of examples there, as we mentioned, the calcium here is going through oxidation, which means the calcium is our reducing agent, while the oxygen here is going through reduction, which means it is the oxidizing agent in this particular case. Any questions on that there? All right. Another example here, we could look at this. And again, this could be a situation where, maybe you don't want to look at sort of electrons, right? So we could use some of the other definition of oxidation reduction to help us decide what's happening. If we look at the carbon on the left-hand side and we look at the carbon on the right-hand side, we can see that as it went from left to right, it gained oxygen, which again is another definition of oxidation. So we know that the carbon is going through oxidation, which means it would be the reducing agent. Now, the good thing on this one is there actually is a metal involved. So there actually is a metal. Spit that out. No. There's a metal over here. And that's tin. If we look over here, oxygen is -2. The tin here is +4 on the left-hand side. Over here, tin by itself is 0. So again, if you weren't sure what's happening with the tin, you could use that number line to help you. It is starting at +4, which would be over here. It is then heading towards 0, which is going to the left-hand side, which will tell us that it is going through reduction. And the tin here is actually being reduced, which means the tin would actually be the oxidizing agent. So again, in this situation, the tin 4 oxide would be your oxidizing agent. The carbon over here would be your reducing agent. So this is, again, another place where, you could use the oxygen hydrogen sort of definition to figure out what's going on. Or in this case, if you couldn't remember that, you could still use the tin part of it. And if you're able to deduce that the tin is being reduced, by default, the carbon would have to be going through oxidation. Any questions on that there? Okay, so just to go over and make sure everybody's on the same page in terms of how we actually do assign oxidation numbers. These are some of the rules for assigning oxidation numbers. And again, remember that oxidation numbers are also sometimes referred to as oxidation states. And it's technically the charge that the atom would have in a molecule or compound if sort of all the electrons were transferred. And again, when we talk about oxidation numbers or oxidation states, they're not always going to be sort of what you envision in terms of charges for certain elements. Again, they may have something slightly different than sort of the charges and stuff you think about when you did like nomenclature or something of that nature. So let's just start with the basic rules here. If you have any element in its free uncombined form, it will have an oxidation number of 0. So that's where we see something like sodium metal by itself, potassium metal, our diatomic guys like hydrogen, oxygen, nitrogen. Again, anything just basically, that's just how it comes from the periodic table, if you will, not combined with anything, will have that oxidation state of 0. So that's how in the previous couple of examples there, the magnesium and the calcium, they both started with a 0 oxidation state. Again, they're uncombined, which is the key thing there. For monoatomic ions, the oxidation number will equal the charge on the ion. So really what this means is if you have something like your basic, for example, iron 3 chloride. This is iron 3 chloride. The iron here would have, like it shows there, a +3 charge. If you had something like lithium chloride, we know that this guy's going to be +1. So the oxidation state of lithium there would be +1 as well. Oxygen, which is usually a pretty good place to start with. A lot of guys do have oxygen involved, which makes sense. It's oxidation reactions happening. They typically will be -2. So it is probably the best place to start if you're assigning sort of oxidation numbers is to start with the oxygen and again assign it a -2. Now with that being said, probably 9 times out of 10, if you do see oxygen or an O in a formula, it is going to be the -2 oxidation state. But there are some situations where it will not be -2. And the most common situation is when peroxide, which is this guy here, this is a polyatomic ion, which is peroxide. And if you do have something that's peroxide, the oxidation state of oxygen in that case is actually -1. So like H2O2, like we got up there, that's hydrogen peroxide. And the oxygen in that is actually -1. The key, how you know maybe if it's oxygen or not oxygen, a lot of times because peroxide is O2 2-, that extra 2 sort of hangs out, or you see that 2 kind of pop up in a couple of places in the formula. And again, that's a good way to sort of figure it out. So anything that's in a standard state, oxidation state 0, anything that's sort of a normal ion in an ionic compound, like it normally would name it, is the charge or the oxidation state. Oxygen, again, usually -2, except, again, if it's peroxide. Continue on with some other information here about that. Hydrogen is going to be +1 in pretty much most cases. It can, as you remember from nomenclature, right, become H-, which is hydride, IDE. And that also is the case for the oxidation number. So if you had something like LiH, for example, again, the Li is going to be +1. The hydrogen would be -1 in this particular case because of that. So if hydrogen comes second in a formula behind a metal, -1, otherwise going to be +1 for hydrogen as you go through there. Everybody in group 1 is going to be +1 in terms of their oxidation state. Everybody in group 2 will be +2. Fluorine will always be -1. Now, when you add up all the oxidation numbers, they do need to equal the overall charge that you have on the molecule or ion. So what that means is if it is a neutral molecule, when you add up all the oxidation numbers, they need to equal 0. If the overall charge on something is like -2, then obviously they need to equal -2. Lastly, not up here, oxidation states do not have to be whole numbers. So you could have something like -0.5, which is superoxide for O oxygen, O2-, not O22-, but O2- as well. So it doesn't always have to be a whole number as well. Typically speaking, if you got oxygen involved, you got sort of 3 elements, good to start on the right-hand side where oxygen usually is, go to the other side and save the guy in the middle for the end is usually a good way of doing that. So let's take a look here and how to properly assign. So if we have HCO3 minus, which is bicarbonate, if we look at bicarbonate, again here I would start with the oxygen, and in this case the oxygen is going to be, let's rewrite it over here, -2. Since there's 3 of them, that does give us a -6 overall. Again, I would leave the guy in the middle for the end, going to the hydrogen, which is going to be +1. Overall, this bicarbonate has a -1 charge, which means to balance that out, if we just take what we got going on at this point, we're at -5. So the carbon needs to be +4 to balance it out. +1 and +4 is +5, and -6 is -1. So when we give the oxidation states here, hydrogen would be +1, carbon would be +4, oxygen would be -2. What people sometimes make a mistake on is they give like the grand total for something like oxygen, and people will write that the oxidation state of that oxygen is -6. So it is not. If you're asked to give the oxidation number, the oxidation state is like you took that one element by itself, the charge that it has. The other important thing is actually that part of it. It's the charge part of it. So you can see that it's +1, +4, -2. So you do need to include the charge when you write an oxidation number. So if you don't do that, it will be wrong. So make sure if it's positive, you put the positive sign. Even if it's positive, still put the plus. And if it's negative, you still need to put the negative, obviously, to indicate that it's positive or negative with your oxidation number. Any questions on that there? Oops, so I think we have some. So why don't you take a couple minutes here and assign the oxidation numbers for everybody here, for each of the elements in each of these guys, and see what you come up with. Okay, so let's take a look and see. So we'll start with the lithium oxide. So really, this is going good place to start is oxygen is going to be -2 in this case. And lithium is group 1, so it will be +1 like normal. So Li would be +1, and oxygen here would be -2 for the first one. Looking at B there, PF3, fluoride always going to be -1. -1 and 3 gives you -3. Overall charge here is 0, which means the phosphorus in this case is going to be +3. So the phosphorus here would be +3. The fluorine would again be -1, not -3, not the grand total. So again, as I mentioned before, this is a situation where you may go, isn't phosphorus always -3 when we do like nomenclature and stuff like that? So again, it's not always going to be exactly the same as sort of the charge we think about it when we think about ionic compounds. Certain things, depending in a non-metal sort of combining, can have either positive or negative oxidation states depending on how they come together. HNO3, which is our nitric acid. Again, in this situation, if we got sort of 3 things together, I would start with the oxygen, which is going to be -2 in this case. This is going to give us -6. Going the other way there, hydrogen going to be +1. Again, nitric acid is neutral, which means it equals 0. So in this case, to balance that out, we're looking at +5 for our nitrogen. So hydrogen being +1, nitrogen being +5, and oxygen being -2 in this case. Again, you see the charge on each of those. And again, just for one individual guy when you do it. Same thing with the phosphorus. We normally think about nitrogen as being -3 when we think ionic compounds. But again, not really the situation here, because really the nitrogen and the oxygen in that case is NO3-, which is nitrate. Those guys are all covalently bonded together. And in this arrangement, again, that is essentially what we come up with. This gives us -6, and +5 gives us -1, which is the charge we associate with nitrate, right? And again, especially in that sort of non-metal covalent bonding situation, these guys are going to have oxidation numbers that maybe don't match the charge we think about in terms of ionic compounds. Lastly here, if we look at the last one, which is dichromate, and dichromate here, Cr2O7 2-. Again, starting with the oxygen, it's going to be -2. That's going to give us -14. The dichromate equals -2 overall. This is a little different since we don't have one chromium here. We do have 2 of them. So it's like 2 times what? Right, equals -2. And hopefully you'll be able to figure it out. It is +6. +6 times 2 is 12. +12 and -14 gives you -2 overall. So in that last one, our chromium is +6, not 12 in this case, but oxygen is -2 in that particular case. Any questions on how to assign oxidation numbers, oxidation states? Really important to be able to do this, obviously, because pretty much in this entire chapter and beyond, I guess, you have to be able to figure out what is being oxidized, what is being reduced, and obviously, in most cases, that oxidation state is going to help you do that. Any questions on any of that there? Okay. So we talked a little bit here about, again, balancing sort of very simple redox reactions. And really to balance simple redox reactions, you basically add your 2 half reactions together, your oxidation and your reduction half reaction. And really the main thing that you need to be aware of when you're doing that is to make sure that, again, you have the same number of electrons in your oxidation and your reduction half reaction, as they should sort of completely cancel out. So again, your oxidation half reaction will show somebody giving off electrons again on the product side, and your reduction half reaction. Somebody gaining electrons over here. Now, in this particular case, you know, if we were to add these together, we do want the electrons to cancel. So in this made up example, they won't cancel at this point. So what you would typically have to do is take this guy and multiply the entire thing by 2. And that would give you, not that, that would give you the top one that didn't do anything, plus my bottom one, which is 2 electrons plus 2b goes to 2b minus in this particular case. And if we added this all together at this point, now our electrons would cancel and we'll be left with whatever I made up here in this particular case. Like that, probably. And in this case, again, this would be our overall reaction and our half reaction. So in a basic, just simple redox reaction, that's essentially the only thing that you have to worry about. You just want to make sure that, again, you multiply by a common number, not just the electrons, but everybody in that half reaction before you add them together. Also, as I mentioned, because one's an oxidation, one's a reduction, the purpose of that is whatever electrons are lost by the person being oxidized should be the same number of electrons that are being gained by whatever is being reduced. So that's why they should always completely cancel out. If you find yourself in a situation where you're adding those half reactions together and they don't completely cancel out the electrons, something probably went wrong somewhere along the way as you were doing that problem. Again, they should definitely completely cancel out. Now, when we do balance sort of redox reactions, a little bit more difficult is the way that we balance them when we're dealing with either acidic or basic solutions. So if you're dealing with acidic solutions or basic solutions, it's a little bit more in detail how we go about canceling them or sort of balancing these guys. So for example, let's take a look at this, this redox reaction here, and we're going to balance it in acidic solution. So this is our unbalanced equation here. And usually the first thing that you want to do is perhaps figure out, you know, what is happening in terms of who is being oxidized, who is being reduced. And again, here we can use our oxidation numbers to help us with that. This is +2, which means obviously the iron here has a +2 oxidation state. This is the guy we just did, oxygen being -2 and our chromium being +6 in this case. Iron on this side is +3 and the chromium is +3 over here. So this sometimes throws people because you're like, I know when I got like a metal and a non-metal together, my metal is going to be the one losing electrons. My non-metal is going to be the one gaining electrons. But now I got like 2 metals happening here. So again, like I said, you can, if you're not sure, just take it to that number line and go, iron started at +2, which is like here. It ended at +3, which is going in that direction. So our iron is actually the one being oxidized, while our chromium started at +6, say over here, and ended at +3, heading in that direction, which means that our chromium is going through reduction. So again, you can sort of simply figure it out that way. And that's important as well. So since we'll talk about a couple of things, since this guy is going through oxidation, that means that this guy will be our reducing agent, while this guy is going through reduction, which means that will be our oxidizing agent in this case. So basically, once you have this reaction in its unbalanced form, the first thing that you really want to do is split the reaction into its 2 half reactions. So you want to split it into its oxidation half reaction and its reduction half reaction, just like that. Really, the simplest way to do that is just to find things that look like each other. So the irons would stay together. Anything with chromium will stay together. Now, once you do that, the next thing that you want to do is you want to balance the half reactions like you would normally balance a chemical equation. That means that you would put a coefficient. And you want to balance everything other than oxygen and hydrogen. So you want to balance all the other elements except oxygen and hydrogen. So when we look at here, we have 1 iron and 1 iron, so we're all good. Over here, we have 2 chromiums and only 1 chromium on this side, regardless of the charge. So to balance out just like normal, we would want to put a 2 in front of that chromium that's on the right-hand side there to balance it. And that's what we did here. So again, to balance just a reduction half reaction, we're going to put the 2 in front of it. The purpose of this is when we are all completely done balancing this equation, it should be balanced really 2 ways. It should be balanced like a normal chemical reaction or equation, which means you should have the same number of elements on each side. And second, it should be balanced charge-wise. And what that means is you should have the exact same charge on the left-hand side of the arrow as you do on the right-hand side of the arrow. That charge does not have to obviously be 0 on each side. It just needs to be the same number. So if you have an overall +2 on the left, when you add up everything that's going on the right-hand side of the arrow, it should equal +2. And it just needs to be the same number. Now, once you have balanced all the other elements besides oxygen and hydrogen, the next step that you do is you balance the oxygen. And the way that we balance oxygen is we actually use water to balance oxygen. So we add water to whichever side needs the oxygen. And that would tell you how many waters you need to add. The problem, though, is for every water that you add, you are not just adding oxygen, but you are also adding hydrogen, which means you need to take care of that. So for every side that gets a water, I'll just go this way, for example, the other side needs to get 2 H pluses added to it. So the 2 H pluses will take care of the hydrogens that you're adding to one side to balance out the oxygen. So again, you won't end up with too little numbers of hydrogen at the end, or not the right number of hydrogen. So in this particular case, if we look at these half reactions, the one with the iron, there's no oxygen, so we don't have to worry about water. But when we come down here, left-hand side has 7 oxygens, right-hand side has none. So on the right-hand side, we would need to add 7 waters to balance out the oxygen. So 7 waters would go to the right-hand side. Purpose is to put the oxygens in there. But because we added 7 waters, we also added 14 hydrogens. So to the other side, this side needs to go 14 hydrogens to balance out the hydrogens that we just added. Any questions on that so far? Now, once we have all the elements balanced, oxygen balanced by adding water, and by the way, if you're kind of short hydrogen to begin with, you could add just H plus to the other side to balance it out. So sometimes you'll come across that where in a half reaction, you're starting with an extra hydrogen on one side than the other. So to balance it out, you could just put H plus on the other side, as many H pluses as you need to balance it out. Once you balance out all the elements, the next thing that you want to do is you want to balance out the overall charge on each side of the half reaction. And we're going to do that by adding electrons, which means you need to add electrons to whichever side needs the negative charge to get us down to the same charge on each side. So if we look at this, really the easiest way to do it is just to take the overall charge. So we had, I'll write the other half reaction there. I believe we had iron going to iron 3. So when we look at iron 2 going to iron 3, what we have going is overall charge on the left-hand side is +2. Overall charge on the right-hand side is +3. So we do need to add an electron to the right-hand side to balance out the overall charge. This now gives us an overall charge on the right of +2, overall charge on the left of +2. It is balanced in terms of the charge. Now, when we look over here, this is +14 and -2. That's a grand total of +12 happening there. On the right-hand side, we have +6 from here and nothing from on the other side, which means that the left-hand side would need 6 electrons to balance that out. And that's what we would add to our second half reaction. Overall charge on the left-hand side now is +6. Overall charge on the right-hand side is +6. Now, I personally think it is the easier move to do it just like I did there. Just figure out the overall charge on each side and make sure that you balance it out. Some people will go individually by the element being oxidized and reduced and how many electrons they're gaining and losing, which is perfectly fine. And you could do it that way if you know what you're doing. But you do have to take in sometimes coefficients into account, which sometimes people mess up on. So really, you know, just so we're clear, when we look at this, for example, you could go individually like we did and go, hey, that's +6, right? And this one is -2. And this chromium, each of them are like dumping +6 or 6 electrons and so forth. But, you know, really the math is all done for you by that overall -2 charge, right? The overall -2 charge is taken into account all those oxidation states. So it's just easier sometimes just to take that overall charge on an ion instead of going individually like this guy is gaining or losing a certain number of electrons. And it's easier to figure out, you know, how many electrons you should add. So, you know, some people are taught to kind of do it individually by each of the elements, what it's gaining and losing. And I've seen a lot of people mess up on that because, again, sometimes there's coefficients or something like that that people forget to take into account. So you'll never really mess up if you do it sort of this way I just showed you, where you just look at the really overall charge on each side and not kind of go individually for everybody and balance it that way. You'll be fine. Now, once we add the electrons, the next thing we want to do is add the two half reactions together. But remember that before we can add the two half reactions together, we do need the same number of electrons in each side. And by the way, we also know that at this point when we added the electrons that we did it kind of correctly, because again, the iron is our oxidation half reaction, which means electrons should be on their product side. And our chromium dichromate here is our reduction half reaction, which means that the electrons should be on the reactant side. So everything's on the correct side. If you're at this point, you add the electrons to the same side. Not good. Something bad happened there. So we do need to make sure we do have the same. So in this case, we do have to multiply the top guy by 6 to get us to the same number of electrons. And if we do that and we multiply the top guy by 6, again, not just the electrons, but everybody that's there, we get 6 iron 2s and 6 iron 3s. Gives a plus our 6 electrons. Now that we got everybody there with the same number of electrons, we can add these guys together. Pretty much everybody on the left-hand side of the arrow will stay on the left-hand side of the arrow. Everyone on the right-hand side of the arrow will stay on the right-hand side of the arrow. Anybody that is opposite sides of the arrow, but maybe not exactly the same, you can reduce down as well. So you could do some reducing if you like. And if we do that and add them together at this point, our electrons again are going to cancel. This is going to leave us the balanced equation in acidic conditions. So if we didn't screw up here and carried everything down, this again should be balanced two ways. It should be balanced both by elements. So if we look at it, we see 14 H's on the left, 14 on the right, 2 CRs on the left, 2 on the right, 7 oxygens on the left, 7 on the right, 6 irons on both sides. Overall charge on the left-hand side, that is plus 14. Plus another 12 is a lot, but we'll go with 14 and 12. That says 26. and a -2 is plus 24 on the left-hand side. 6 times 3 is 18 positives on the right, and 6 more is plus 24 on the right-hand side. So again, this would represent the balanced equation. This would represent the balanced equation for this guy in acidic solutions. Any questions on that there? Now, if we want to balance this in basic solutions, what we would do is at this point, we would add OH minus to both sides equal to the number of H pluses that we have. So just to kind of show you that, if we were going to do basic, I'll just use this empty spot here. So if we want to do basic conditions, we need to add OH minus to both sides equal to the number of H pluses we have. So what that means is if we look at our guy in acidic solution, we have 14 H pluses, which means what we would add to this reaction to do it for basic conditions is we would take 14 OH minuses on the left plus our 14 H pluses plus our Cr2O72 minus plus our 6 iron and we would also add those 14 OH minuses to the right-hand side. So for basic conditions, OH minus gets added to both sides. To the side where you added the OH minus and there's H plus, these guys will come together to make 14 waters. And that's good because on the right-hand side, we have 7 waters, which means 7 of those waters will cancel. And we will be left with 7 waters on the left plus Cr2O72 minus plus 6 iron 2s, 6 iron 3s, plus 2 Cr3 plus, and our lucky 14 OH minuses there. And if I still have not screwed this up, it's a 50-50 chance some days, but we'll see how we did here. We should still be balanced the same way in terms of elements and charge. So that's 14 H's on the left, 14 on the right, 2 CRs on the left, 2 on the right, 7 oxygens and 7 more gets you 14 oxygens and 6 irons on the left and right. Overall charge on the left-hand side plus 12. And what we got there? Minus, my bad math there. This was iron 2, right? So plus 12 and minus 2 is plus 10. That's plus 18. And plus 6 more. It's a lot of math there. So we got 18 and 6 is 24, less 14 is plus 10 on the right-hand side. I should really grab my calculator. So this would be balanced in our basic conditions, and this would be balanced in our acidic conditions. Any questions on how to do basic conditions? I would recommend this approach as well. It's just a little bit neater in the sense of waiting to the end to add the OH minuses if you need to. And again, it's equal to the number of H pluses there. You can do it in the middle, like after you add the electrons or before you add the electrons, you could add all that OH minuses, but it gets a lot of combining and reducing down in the middle. It gets a little messy, so I would recommend waiting to the end. Also, just from what we've been talking about in terms of acidic and basic things, we know this is like acidic conditions because we see H plus, right? We also know this is like balanced in basic conditions because we see OH minus in the actual formula as well. Any questions on those steps there? And again, I don't know, maybe review, may not be review. Again, some people cover it a lot. Some people kind of skip over it. Some people do like a little quickie cover of it. So hopefully, hopefully this will help, I hope. Yeah, I'll say yes. That's probably the easiest way of doing it is to balance it acidic first and then add the OH minuses. There is another approach, like when I went to school, they would have you actually, you could add the way I would learn way back when, is right about here at this step. Sometimes people will add the OH minuses at this step. Same deal, equal to the H pluses. But at that point, you need to combine waters, reduce down waters, and stuff like that. So, it can get a little bit more, I'll say, confusing, or a little bit maybe more areas where you could get into some trouble if you don't reduce down correctly, if you kind of do in the middle. But usually, if you wait to the end, it's a little bit easier because there's kind of less stuff that you have to reduce down at that point. But yeah, definitely do the acidic first and then roll it into the basic. All right, so why don't you guys try one and make sure. So why don't you do this one in basic conditions? So there you go. There's the unbalanced reaction. So balance this in basic conditions and see what you come up with, and we'll talk about it. Okay, so since we're getting to the end here, why don't you, if you haven't finished this one, why don't you finish it up tonight and have it done before lecture? And while you're at it, why don't you do the why don't you do the next one as well? And just to make sure again that you're understanding, actually, there's two more I think after that. So why don't you do the next couple of examples of balancing these redox reactions, and then tomorrow during lecture at the beginning we'll go over them again. That way you could check to make sure you've got them correct and stuff like that. So tonight before lecture tomorrow, why don't you finish those next couple of examples, including this one, and then we'll go over them again just to make sure everybody's on the same page, everybody balanced them correctly, and we'll finish that stuff up tomorrow. And we'll obviously continue on lecturing tomorrow as well. So we'll stop here for now for lecture. We have lab today, which I think is group 2 unknown and known, known and unknown, group 2 qualitative analysis. So we'll watch that, and just kind of like group 1 there, you will get, sort of your own unknown, and you have to watch your video and all that kind of stuff and correctly identify it, hopefully. All right, so let's take a little break. We'll start about 3-ish there in the lab, and make sure you put here if you have not done so already. And I'll see everybody in about 10 minutes or so.